Okay, if I can have your attention please, we shall begin. Before I introduce our speaker to you today, I have a quick announcement to make about another event coming up here at Sonoma State. During the spring break week, there is going to be a large meeting on gravitational waves hosted at Sonoma State, part of which includes a public lecture which will be open to a lot of members of the community and those who are interested. So for those of you on our public mailing list, I will be sending around this flyer advertising the talk on Tuesday, March 20th from 7 to 9 p.m. The topic is Listening to Einstein's Universe, and it will be a presentation of some materials that have been prepared, so sort of audio-visual materials for you to experience. But the benefit is that the people who've actually made these discoveries and worked with them will also be there in person to hold a panel discussion and answer questions and interact. So I think that's a wonderful event coming up for us on campus. Again, I'll distribute this to the public mailing list for those who are interested. Our speaker today is also another person I can introduce you to who is right here at Sonoma State, which is always a wonderful thing when we can have someone with the wonderful experiences and contributions that have been made so far. Our speaker is Dr. Aurora Peticolas, who obtained a PhD from the University of Alaska in Fairbanks, followed by her postdoc work in education at the University of Berkeley. When asking her what I'd like to include in the introduction, she very kindly said that most of what you need is included in the slides. So thank you very much for doing my job for me. I'm always happy when that works out. And let's have a warm welcome for Dr.
Thank you, Tom. And I also want to thank Lynn Kaminsky, who I work with here. And I started about 5 months ago or so. And so I will eventually get to the Eclipse part, but I'm going to introduce a little bit about my career, how I got here. So I'm going to start actually in my undergraduate degree, which was from the University of Oregon. I grew up in Eugene, Oregon, so I was a hometown gal, and they had a pretty good physics and astronomy department there, so I thought, well, I'll just stick around and have to pay a lot less to go to college. This is the physics department that got built right before I went there, so it was really nice to have this new building. I had a lovely experience there and got my physics and math degrees at the Honors College and also through the Honors College. So instead of a BS, it was a BA. And I did that because I also like art and literature and creative writing. Even though I'm not great at writing, I like it and appreciate it. And but after that, I was the only woman graduating in my graduating class with a physics degree. And I thought maybe there was something wrong with me. What I discovered is there was something wrong with other people. So I took a little bit of a break after my undergrad, and I decided I wanted some adventure. I grew up skiing. My mom was a ski instructor, so I went to Colorado and was a ski bum for a little while. And that was amazingly fun. And the people I hung out with at the ski mountain said, hey, you should come up to Alaska and clean fish, because that's also fun. And I was young, and I thought, that does sound like fun. Now, on retrospect, it doesn't seem so fun, but I had this VW bus, and we drove up, and so here's my VW bus. And we were driving up to Alaska, and it was the first time I ever saw the Northern Lights. So I was driving through Canada, and we looked up, it was night, and there was this green band in the sky that was glowing like fluorescent lights. And I had heard about the Aurora a little bit from my mom because she grew up in Aurora, New York. So she told me a little bit about it, but I had no idea that it was going to actually look the way it did. It kind of blew me away, and we stopped. Ooh, what is that? So I think that's the Aurora. So I went out, cleaned fish. I got tired of cleaning fish. And I thought, I really miss physics. I wonder if they have a physics department in in Alaska, because I'd fallen in love with Alaska, and I really wanted to stay up there. So sure enough, they had a physics program in Alaska at the University of Alaska, Fairbanks. And I had a marvelous time up in Alaska getting my PhD in physics. And this is the Geophysical Institute. This is me with my ski-joring dog, my dog. I would ski-jor, so I had skis, and my dog would pull me in the snow. And she loved that, and I loved that. And we would go The most hardcore trip we ever took was in 20 below weather out in Denali National Park, and we, some friends of mine and I went camping for one night, and that was the last time I camped in 20 below weather. That was cold. I had to snuggle in with my friend Carrie. We got in one sleeping bag. It was a double, but still cuddled up together with our dogs. So we had all our dogs near us, and then we skied back out. This is my advisor, my PhD advisor. His name's Dr. Dirk Lumersheim. He's retired since then, but I just want to also do a big shout out to him because he was really supportive of me in my PhD and really pushed me hard, but was also really compassionate and could see what I could do. So what I ended up studying for the most part was the Aurora Borealis, which is what you saw there in the picture before. And the aurora takes place up in the thermosphere, which is part of the atmosphere that's especially hot, but it has very low density. So if you were to put your hand out, it would feel cold because there's no atmosphere to actually transmit that heat. But it's called thermosphere because it's so hot. The therm comes from the hot. And it's well above the mesosphere, stratosphere, troposphere. Of course, we live down here in the troposphere. And the aurora occurs about 100 kilometers up or 60 miles up from Earth's surface and is affected by all sorts of things, mostly space related, like space weather, we call it. One of the things that was really cool about studying the Aurora Borealis up in Alaska was that you could actually see it. And so my office was, well, first it was over here, and then it was over here. And then during that time, there was a ground meter. So I don't know how many of you have seen a how do you say it? A seismometer, thank you. A seismometer. Any of you seen the seismometers? Did you used to have one here? Yeah. So, you know, when you have an earthquake, you've got the needle and it jiggles. Yep, exactly. Well, we had something similar up at the Geophysical Institute, but it was for ground currents. So in the ground, if you have electricity flowing through the ground, you can detect that by putting some copper and aluminum posts in the ground and wiring each one up to a needle that then moves as you get electrical signals in the ground. And it happens that when you have Aurora Borealis overhead, there's electrical currents that are in those aurora, and they actually create these huge magnetic fields that then induce electric fields in the ground. So those of you who are taking electricity and magnetism, you'll have learned that. And if you haven't taken that yet, you'll learn it when you do. So it's this crazy thing. All the electricity in this room creates magnetic fields. Those magnetic fields, if they're changing, can then make electricity move in wires. So it's well known for, there's a big oil pipe up in Alaska, and it has all these electrical currents that run through it due to the aurora and actually corrode that oil pipeline, which is a concern. So these things have very practical uses. For us, having this meter, electrical current meter, basically just told us when there was aurora outside. So being dutiful graduate students, we'd stay up all night studying and doing research. And someone would walk by to go to the bathroom or to see another grad student, and they'd see something like this. And then everybody on the floor knew there was aurora, and we'd, get up, go to. So back then, this is not true anymore, but we would go to the roof. You're not allowed to go to the roof anymore, of course. Good old days. So we'd go to the roof, and then we could see the whole sky, and we could watch the aurora moving back and forth. And just, it's so dynamic and awesome. Well, the other nice thing about when I was going to graduate school is that there was really active research about the sun. And if you look at the sun with a sun spotter here on Earth, or you project an image of the sun onto a surface, like a piece of paper, then sometimes you'll see these black spots on the sun. And guess what they're called? Sunspots. Yeah, sometimes our lexicon in science makes sense. So these are sunspots, and what we've learned about them through essentially this line, a line of light called Zeeman splitting, from Zeeman splitting. Anyone heard about that yet in your physics classes? All right, well, we can use that to study the sunspots, and what we learn is that they're magnetic. Otherwise, you wouldn't get Zeeman splitting. So in a very crude way, you can think of them as the magnetic fields that are coming out of 2-bar magnets. Again, this is not quite accurate because it's electromagnetism that's happening, not bar magnets. But you get this dipole field, a south pole and a north pole, out of these sunspots. And from these sunspots, you get these very strong magnetic fields in that loop between the south and north poles. And when we look at the sun in the ultraviolet light, which of course our eyes can't see, but we know exists from our skin gets tan from this light, and all sorts of things happen with this light. It also gets blocked by the atmosphere, luckily, because otherwise we'd all fry, and we don't like that. I don't think you like that either. But what you can see in the sun, in the ultraviolet, are these giant loops. And they are these magnetic loops. They're essentially magnetic loops made visible. And so these are it's more evidence that these sunspots are magnetic. And what's really cool about these loops is that they develop and they change over time. And they can change on the time scales of I'm not sure down to millisecond. Well, there are features that are changing on the millisecond time scale. But they also, the big features can last as long as several days to a week. Yeah.
Just a good question. I'm just curious. What made people realize that the sunspots were magnetic?
Right. Good question.
What instruments were used, or what observations were made to be able to be like, oh, this is what I think is happening, and then to be able to use evidence to support the claim?
Right. And you're asking a history question, which I'm not sure the exact timeline of the answers. Maybe someone in this room does, but there are several things several kind of hypotheses or ideas that came up that were tested over time. And so these sunspots, there's this really famous event called a Carrington flare. And so there was a scientist named, his last name was Carrington, and he lived in England. And he was studying these sunspots, and he had projected the image of the sun onto a piece of paper and was drawing them. And it just happened, because these sunspots it turns out they can flare up, and actually white light can come off of them. And it just happened that he was drawing the sunspots when that bright light happened. And so that was weird and strange and cool. And he wrote a paper about it. And he was the first person to kind of recognize this thing called a flare. And because it looked like a flare, just a flaring of light, they called it a flare. So that was one event that happened to give kind of evidence that there was something dynamic happening in very high. I think that happened over a couple hours, this flare-up. The other thing that happened is that people started recognizing that there was a connection between these flares and sunspots and things that happen on Earth, like the Aurora Borealis would change. And so scientists said, wait a minute, if there's something happening on the sun, and then there seems to be something happening on Earth, maybe there's a correlation between these things. And so some really smart scientists started modeling the physics of the sun, and they realized that the sun must be so hot that the electrons couldn't stay on the atoms. And so it must be basically an electric gas, which we call a plasma. And what we know about plasmas is electromagnetism had been discovered by then. Kind of all of this happened, a couple years, 30 years apart or so. So scientists sat down and realized, okay, if you have this if the sun is a plasma and it's electrical, and we know that electricity and magnetism are connected in the way I was describing before, then we know the sun must have magnetic properties. And then we knew about Zeeman splitting from lab results. And so people said, oh, well, maybe we can study the light of the sun in this particular area, wavelength. So they then basically put a spectrograph at the sun that could look at these lines that only come from when you have a magnetic field. And they saw that indeed, in these regions, you got really bright light from that particular kind of light, the Zeeman splitting light. So that's a very long answer to all the evidence that can go into these things. And I don't actually know the timeline of how that all, the puzzle pieces got put together, but those are the pieces. And it takes a lot of people and a lot of scientists doing the math and the physics, the kind of theoretical physics, and then people doing the observations and people doing lab work, and to really make these big discoveries. Great question. So now, I'll tell you more about that in a minute. What we've learned since then is that the sun has this solar wind, and that is one of the things that connects the sun to Earth. And that's one reason when the sun does something, we see the northern lights change or the aurora borealis change. This is a picture of the solar corona. And again, you can see these loops. Now this loop here, this is the edge of the sun. And so this is a relatively small loop compared to the sun. Earth would be about this big if we could move it to the sun, which we don't want to do, right? So the scale is huge. Now this is a picture that's taken from Earth of the sun with the moon blocking the sun, the bright disk of the sun, which is called the photosphere. And here, this little area here is, you can see how it's red, and that red comes from hydrogen, a certain line in hydrogen emission, and that is about the same size as this loop. So just for scale. Now what you see here, these giant features, and these are called coronal loops. They're very large and they span out into space, and in fact these are also plasma, and they go out into space and they interact with Earth's magnetic field. And so we call, when it kind of gets far enough away from the sun, it becomes the solar wind, and it goes all the way out past all the planets until it hits the interstellar medium. Basically when the pressure of this plasma is equal to the plasma pressure out from another star, then you get this little boundary. And that's a cool area. And Voyager, NASA Voyager, has actually gone through a couple of those boundaries. What that means, we're not quite sure. So we know NASA has many satellites up studying the sun. So these were and are a couple of them. Wind is no longer operational, and I think it's Stereo B that is not operational, but I don't remember. One of these is still operating and the other's not. And they're just a couple examples of satellites that are orbiting the sun along with Earth to study it. And some of the pictures that come back, this is actually from another satellite called SOHO. And what you can see here is, again, the solar, the coronal loops, basically, and they reach out and become the solar wind. So again, this is up in space on the spacecraft. There's a disk blocking the bright sun on the spacecraft, and so that we can see the atmosphere, what we call the atmosphere of the sun, or the corona, and then you can see the stars in the background here. And that's one field of view, one instrument, one camera, and this is another camera or another field of view. And you can see more space here, so it has a bigger field of view. And again, here's the disk. And right here, does anyone know what this might be? It's part of the satellite. That's right, it's holding the disk. So it's just like an arm. Like if you put your thumb in front of a light, then my arm has to hold my thumb, right? Same on the satellite. You have to have something holding the disk that's blocking the disk, so blocking the sunlight. And again, you see all these different stars.
What wavelength of light is this?
This is visible. Hmm. And so is that. It was just colored red so that when scientists look at these, they can go, okay, that's that instrument. But they're both white light. So I'm going to take you back to graduate school, because back in graduate school there was this satellite called ACE, the Advanced Composition Explorer, and it had just, the internet was kind of new, and they had just gotten online a way to share the data from the satellite on the internet, on the web. And so we could see how the solar wind was changing. These are essentially plots of the magnetic field of the solar wind, because the solar wind's a plasma, it has a magnetic field, and the plasma pressure or density. So just like you have density and pressure on Earth and different atmospheric pressures, out in space you can calculate the same for the plasma. And so here they have different. It's not super important, that graph. It was to remind me. And so when I was sitting in this office, we would open up the ACE data, and we would say, hey, I wonder if when ACE sees something in the solar wind, if we're going to see aurora. And we started to see some patterns, just because we had that beautiful electric current set up, and we had this real time. This was essentially real time. I think it was pretty fast that we would get the data in from the satellite and on the web. So we started making these correlations between what was happening on the sun, the solar wind would hit the satellite, and then we would get to see auroras. And it would take a few hours before the solar wind would hit Earth. And so people would notice, and they'd say, hey, did you see that big pressure pulse that's coming in, and the magnetic field was pointing down? And so we kind of figured out what would then give us aurora. So it turned out that if the magnetic field was pointing southward and we had big pressure pulse, that we would see aurora. And so then we could predict. So then we didn't have to wait for our electric current. We could use our satellite, NASA satellite out in space. So that was really cool and fun. And then, of course, we learned about the auroras, and that was what I was studying for my PhD. So this is just a quick overview, which essentially what happens is that electrons come down just like a fluorescent light. You have electrons go in a fluorescent light and bombard the atoms, and they get excited. And then when they relax, they let off light. And that's the same thing happens in the atmosphere for aurora. You have these electrons that come from space, and they interact with the upper atmosphere. It excites. That's literally that's the scientific word. They're excited, and then they relax. And in the relaxing, they let off light. And it's mostly oxygen giving off both red and green light. When you have really active aurora, it's nitrogen, molecular nitrogen and oxygen. And these electrons, they're within our Earth's magnetic field. So if you could put on magnetic field glasses and look out in space, you'd see these big lines. Or if you could take iron filings and throw them out into space, they would align in a big bubble like this. A friend of mine and I like to call it the octopus in the sky. Or you can call it the magnetosphere, which in scientific conferences is probably the better term. So what's interesting about this is it's kind of a little jail for plasma, in that when an electron or a proton, things with a charge, when they see a magnetic field, they get pushed counter to the direction they're moving. So you have, those of you who've taken some of these classes, if I'm an electron and I'm moving this way, and you have a magnetic field pointing this way, and it's V cross B. So we have right-hand rule, V cross B, right? And then I get pushed this way. If I do that, it's been a little while. Right, so I'm trying to go this way, but because there's a magnetic field, I get pushed this way. Wouldn't that be annoying? If we were charged particles trying to move in the world, we'd get turned around and couldn't move. We'd be like, oh, someone turn off this magnetic field. All right, so that's what it's like out in space for all these charged particles. They spiral around these magnetic fields. And so some of the solar wind will come into the magnetic fields and some won't. But the big idea is that the solar wind is pushing from this side, blowing, and it exerts energy. It basically has an energy exchange between the edge of the magnetic field and the solar wind. And it exchanges energy. And in that energy exchange, it creates electrical currents in the magnetosphere. And those electrical currents then turn on the lights. Which lights? The Aurora lights, that's right. Very good. I just had to show this. UCLA made a wire model of this. They have a space plasma group, and I think it's kind of cool. It's the only reason I showed that. Also, it kind of does a good job showing the 3 dimensions of it. It's not just a flat 2D thing. All right, so after I got my PhD studying the Aurora Borealis, while I was there were scientists coming up to Alaska to launch rockets into the Aurora Borealis, and they were coming from the University of California, Berkeley. And I thought, wow, you guys are doing cool science. I want to do that. And they said, okay, come do it. So I got hired at this lab to study the Aurora. And I started working with scientists who had studied the auroras for many years, and they had never seen the aurora. So that just goes to show you don't have to see things to study them. But it helps, I think. This was the mission that I worked on, the Fast Auroral Snapshot mission. And I loved it, it was great. But I really always wanted to do teaching. I wanted to be involved in teaching, and there was an education group at the lab, and I started working with them more and more. And then eventually I ended up leading the education group, and then we changed our name to Multiverse at that time. And this is their website, Multiverse. So this is where I came from in October, and now I'm here. Yay, I'm very happy to be here. That was very nice too. I was there from 2000 till 2017. That's a long time to be in one place. It's ready for some change. While I was there, in the last couple years, the last 5 years, I was working on this Eclipse Megamovie project. So the last 20 minutes of my talk will be about that, 15. And we had envisioned this project where we got people around the whole country to take pictures of the solar corona from Earth when the moon blocks the sun in 2017. And we started working on it in 2012. And we had all these great ideas. We got a little bit of money from the National Science Foundation. We tested it in Australia. We went, wow, that was a lot harder than we thought. Yikes. What we really need is like a Google or Microsoft or some big company, Apple, to work with us. This is how it works. You go, what I'd really like. And so we just kept saying that for like 3 years. And then one of my colleagues at UC Berkeley, Dr. Alex Filipenko, he was out to raise money for an observatory called Lick Observatory. He had taken time off all his teaching to raise money, and he had run into this Google team, the Making and Science team, and he was talking to them about Lick, and they said, yeah, we really like what you're saying, and we want to sponsor that work. And they said, well, do you work with any folks that do education and outreach? And he said, yes, I do. And so he contacted us and said, Laura and Dan, another colleague of mine at Berkeley, would you like to come down and meet with this Google Making and Science team? And I said, no. Just kidding. No, I would never say that. We said, what? Yeah, that sounds great. So we went down and talked to them, and we pitched them all these different ideas, and one of them was our Eclipse Megamovie project. And they said, ooh, that's cool. So then we started meeting with them regularly, and it ended up being a full-blown partnership to do this project that I'm going to tell you about. And it was a very large project. We ended up, after 3 or 4 years, having all of these people working together with us. I'm not going to read through it. You can read through it. Just know there's a lot of people to thank. It was a big project with a very small budget, so a lot of us did some volunteering on the project as well. One of the nice thing about this, having Google as a partner, is they have resources. And they gave us some money, which was wonderful, and I'm so grateful for that. And but they also had all these resources. So they had this little video created while we're trying to recruit people to take pictures. So this was a video that we then sent out to various places, news, the press, to try to get people to sign up. So I'm going to play it.
On August 21st, 2017, something really cool is happening. For the first time in almost 100 years, a total solar eclipse will be making its way across the United States. It's going to give scientists an amazing chance to study the sun's atmosphere. And while that's making history, there's something else making history too. You. We're making a film from thousands of pictures taken by citizen scientists, and we need your help. We're hoping if you're anywhere along the path of the total eclipse, you'll snap some photos. We're particularly interested in the moments where the sun is totally eclipsed. The data we get will allow scientists to study the sun's atmosphere for years to come, helping them to understand motions in the corona, cyclical changes in temperature, and much, much more. To find out how you can be a part of the project, click on the link below. Thanks, and happy viewing.
So I think that gives a pretty good overview of what we were trying to do. And we also, various members of the team wrote articles, got out of the press. We used the Berkeley press machine to get press releases out. We went on a tour across the United States to try to get people interested, and we went to gyms like this in the middle of rural America, which was interesting because, as you may know, rural America is very conservative and Berkeley's very liberal. And our president had tweeted some very bad things about Berkeley, and rural America had heard about that tweet. And so we showed up, and in fact there was one town we were not allowed to come to because of that. And so, but what was awesome about this is that in many towns we were able to actually have conversations about that event and the political divide in our country. So we'd sit down with people, a mayor in a bar, and we had those conversations about, you know, what actually is happening at Berkeley. What do you believe? What do I believe? That was an unintended consequence of this tour. And meanwhile, we taught about physics and got people excited about the eclipse. And we showed videos like this one, so I'm going to show you a couple educational videos. So this was an animation made by the Goddard Space Flight Center Visualization Studio. And what you're doing is, the point was to look from space, what's called the L1 point, Lagrangian point, at the shadow as it moves across the United States. So then you can see the red line is just an indicator of where the shadow had passed. So you see that it traveled all the way across from Oregon through Nebraska, all the way through Tennessee, north South Carolina, and left South Carolina. How many of you saw the total solar eclipse? Okay, many of you in here. Fantastic. Yes, I know. My poor kids, they were back here. They were offered to come with me, but they did not. Okay, and then here's another animation that a colleague of ours down in Texas made for planetarium shows, but also made a flat version that I thought is really nice. So the sun is above this animation, and the shadow's not real, but it's just there to illustrate kind of the shadow that happens out in space.
When the new moon passes exactly in front of the sun, its shadow crosses the Earth. The deepest part of the shadow is called the umbra. People in the umbra see a total solar eclipse. It takes about an hour for the shadow to cross the Earth. 2 weeks later, the full moon can cross into Earth's umbra. Since the Earth is 4 times the diameter of the moon, the umbra is also 4 times larger, or 16 times the area. So, lunar eclipses are more common than solar eclipses. Everyone on the night side of Earth can see a total lunar eclipse, but only people in the narrow strip of totality can see a total solar eclipse. So, not only are lunar eclipses more common, more people can observe each one.
Yeah, I really like that one. And then there's one more for those of you who did not see the total solar eclipse. This is what it would have been like.
First contact is when the disk of the moon first starts to cover the sun. During the partial phases, you must use solar filters or projection techniques to safely observe the sun. It takes about an hour for the moon to completely cover the sun. The last bit of the sun is the diamond ring. Second contact, totality. Third contact, put it back on your filters. The last hour, the moon gracefully exits, uncovering the sun.
And what's the last contact called?
As
Fourth.
the last bit of the moon leaves the sun, it is fourth contact and the end of the eclipse.
All right, so that's what many of us got to see. These are some pictures of our volunteers that were taking photographs across the U.S. And this is some of the types of equipment they had. So they all had their own equipment, and we were asking people with DSLR cameras because we wanted some real high-resolution images with some really nice telegraphic lens. Did I say that right? Telephotograph. Thank you. my brain. And here you see there's a filter on for practicing. This was Dr. Brian Mendez, another colleague of mine there at Berkeley, did some of our testing for us and helped train some of the volunteers online. And this is his setup, and he has his filter there for observing during the partial eclipses, so he doesn't burn out his CCD on his camera. Afterwards, one of our volunteers took all the data that was uploaded onto the Google server, and then it's available free. I'll tell you a little more about that. And made this map for us of where all the images came from. So you can see that we were successful in getting volunteers and covered that path very nicely. I think I can show this, I'm not sure, but it's a little embarrassing. Which those of you who might have seen the total solar eclipse will know. It's very exciting, you don't even realize what you're doing. And I happen to be a loud individual, as I'm told often by my friends and family. And this movie, okay, yeah, I think we're not going to show it. I thought I had it in here. But there's a video that they made, a little documentary of my trip in Wyoming. So if you're interested, if you do a Google search on Eclipse Wyoming Megamovie, you'll see me. I'm not going to show it. In any case, you don't need to see that. And then here, but just to say that when you do see a total solar eclipse, it's, and I know many of you here saw it, but it really is, it's just outstanding. Like, you can't even describe it. I was shaking for 10 minutes afterwards because of all the physiological changes that happen. The temperature decreases, I got cold, it goes dark. You see this thing that looks like, I mean, you can't even capture it. All of these pictures are photos that Brian took with different exposures, because our eyes are these amazing things that have this great dynamic range. And if you want to replicate what your eyes can see, you have to take pictures in all these different exposure times and then put them together to even kind of see what they look like. So that's what Brian's camera did here, is it took a bunch of exposure times and then he compiled them into one really nice photo to try to capture what it looked like. But even this, those of you who saw it agree, it's just not even, right? It's like, yeah, that's cool. And there's another eclipse coming up in 2024 across the US. Plan to see it. That's all I can say. And this is the star Regulus right here, which is helpful in analyzing the data. Remember these pictures I showed earlier? So we went around during our tour and we said, what's so cool about all of you taking photographs is that you can do something NASA can't. Because what NASA can't do is get the solar wind and the chromosphere and the corona from this white circle all the way out to here. Because what's happening here is it's just too bright for the instrument. Or you can make it so it's not so bright for the instrument, but if you get too close, there are two problems. One is you have to stabilize the satellite so much that there's no wobble, because if there's any wobble, then the light will just peek over the disk and destroy your instrument. And the other problem, if you have a disk that's the exact disk of the sun out in space, is you'll get this crazy diffraction around this disk because it's very close to the camera. And that will mess up your data as well. So what's fantastic about the moon is it's really far away from us taking photographs, so diffraction's not a problem. And we're very stable here on Earth. We're not going to have any wiggles, thankfully. And so that we kept saying, someday, when we get these images, we can compile them with the NASA data. And we can see between the sun and the NASA data. And you'll help us. So Brian did this great thing for me. Well, I guess he had done it on his own, but he gave me this image. And then he had already put them on. And so here they are. So these were the images taken at this time when the NASA data was taken. And so you can see we're filling in. Here's the beginning of this the streamer and these streamers here. And you can see there's also this little loop here. There was something called a coronal mass ejection, which is this big ejection of mass off the sun during the eclipse. So we get to study that. And we can look at it by combining these kind of images.
Where was it when that happened?
With this picture?
Yeah, was it halfway across the Earth?
This was in Oregon.
It was Oregon.
Yeah, Eastern Oregon.
Yeah.
Was he from? Yeah, just over the Cascades. So we had 12,749 users sign up, meaning that they signed in with a Google profile. 1,370 volunteer photographers signed up before the eclipse, and we trained many of those. 593 of these submitted photos, and 597 photographs submitted photos post-eclipse. So in total, we had 50,000 photographs, and it's about 700 gigabytes. In total, we had almost 1,200 photographers contribute. A resounding success, especially because I was told often, this will never work. This will never work. I'd go home and go, what am I doing? What am I spending my time on? But it did work, and I knew it'd work. And so one of the things I like to show in this process is that this giant kind of citizen science, it was more a crowd-sourced data investigation, was and is part of the scientific methodology. And I'm sorry that this slide is kind of ugly, but nothing's lining up. But I wanted to show this a little bit since we're in an educational setting and there's a lot of discussion right now on how do we teach about science and how do we teach people about the process of science and scientific practices. So these are some of the kind of practices of science, asking questions. So for this project, we asked how will more solar atmospheric density data help our understanding of the sun? And so that's what's really unique about these eclipse data. We created a plan. We wrote and published this Eclipse Megamovie white paper, which kind of gave us a rough idea of how we were going to make this happen. We did our test in 2012, learned a lot about how hard it was going to be, revised that investigation plan, got the partners we needed involved. We carried it out, recruited volunteers, developed our website and app, collected photographs, and we are now here analyze and interpret data. So one of the tricky things is to do science. There's all this kind of things you have to do to the photographs. So we're in the middle of that, and then we'll be constructing explanations, using models, computer and math, communicating results. And so this is a long-term project. And so far, here's some of the things we've done. This is an analysis of an image we've done using a published algorithm to basically enhance the image so you can see many of the features as you can. So it's just one image, and you can see that there's a lot more in those one images than you could see without the analysis. And we're really interested in looking at kind of the whole structure of the corona and how it changed over that hour and a half that the shadow crossed over the US. There's one of our team members, he's like one of the three people on the planet maybe, that studies the size of the sun. And it turns out it's really hard to know the size of the sun accurately because the sun is, it's a gas essentially, so it's moving up and down, it has seismic activity in it, it's changing all the time. And these Bailey beads give us some understanding, since we know the features of the moon so well, that when the light peaks over the moon craters, we can get better data about the size of the sun. As I said, there was a coronal mass ejection that happened at 1724 UT. That was around the John Day, Oregon shadow, when the shadow crossed John Day. It happened for a while, so that was kind of the peak of it. That's when this photograph is. And this is a photo of the SDO of the AIA, which is an ultraviolet imager from the SDO NASA satellite. So it's a real big zoom in on the sun, and this is essentially a sunspot. And it's but because it's ultraviolet, it's bright in the ultraviolet. And there was a flare up. So not only did we have a coronal mass ejection, we also had a flare during this total solar eclipse, which blew all of us away, and it blew out from the sun. So we're very excited about that, and I'm going to show you a couple pictures here. There's the flare actually flaring in another wavelength on this camera, on the spectrograph from this camera, and another one. And then this is the RESI data, which is in X-rays, and there was a little bit of X-rays coming also from this flare. So we're in the middle of trying to make sure that we know the pointing of the images, that we know what we really want to know from this data is what is the brightness. So if we can calibrate these images so we can say right here is, it's a negative. So this is actually the really bright area. And if we can put a number to that brightness in terms of flux, then we can get a density of the plasma as you're looking through it. And that's a really hard thing to get normally, and it's not something we get often. And now we have 50,000 images and some of those we have what are called flat fields and darks. We have some of those so we can calibrate, and then we can do a big calibration over the whole data set, but that all takes time, but we're doing it. So we're excited. And I'm almost done with my slides. So, in summary, you can have access to this data. Did any of you contribute to this data set? Do we have any Megamovie volunteers here? All right. But all of this is open source. To be a volunteer, you had to agree that your image would be freely available to the public with no credits needed. So it is now available on these 3 different platforms: GitHub, the Google Cloud platform. GitHub is where you can get all the data, all the analysis tools that we've developed thus far. Google Cloud platforms where you can get the images themselves. There's a SQL database. You can go in there and get it all, or you could get some of it. You can search. And Zooniverse is a citizen science platform to start helping us do the analysis. All right, thank you very much.
Do we have any questions from a speaker? Steve?
Were there any dedicated polarization movies or sequences that were done from sources behind the sun?
Not as part of this project. I'm pretty sure that there were some done from some NASA funding and maybe NSF funding, but I don't know those. I have heard inklings of that, but.
And the LEDs, so those are shadows of the craters
No, they're essentially,
on the moon?
it's, if the moon was almost nearly blocking the disk of the sun, right? But then you have a little crater, so it's just as it starts to block, then it will block the outside of the area will block the disk, the photosphere first, but you'll still have this little part that doesn't block the photosphere, and it essentially just allows that light to go through.
So it's a little peeking through.
It's a peeking through the photosphere, exactly.
And we know the depth of the craters. So.
And we know the depth of the crater to very high because of LRO, NASA satellite, and we have all our volunteers also had to have GPS associated with their images, so we know where they are and their timing pretty well as well. So we know then the angle of the moon, the orientation of the moon with respect to the viewer, which also is important because the moon's changing, the orbit's changing, we're changing, right? So the features of the moon actually change, or the crater angle changes over that hour and a half for each viewer, yeah.
So what kind of quality control do you have to do with the data since it's kind of open source and that kind of stuff?
Yeah, no, that's a great question.
So I was thinking, I really like the idea of this open source data, but then I thought, well, how do you know if something is legit or not?
Yeah, no, I didn't even get into the whole movie part. And part of it's because we had hoped that we might get a better movie. There is a movie you can look at where we were stitched together a bunch of these images in real time that day, which turns out to be way, way harder than anyone thought. And if you think about it for a little bit, you'll understand why. And it's in part what you're saying. So we had images that were small and large and big, so all the circles, we had to find a circle, fit it, and then make all the circles the same, right? So that we managed to do because we had tested that on the 2012 data set. But what was interesting is we had kept asking our Google colleagues, can't you do some machine learning on this? Like, look at enough Eclipse images and so we can kind of do all the sorting and rotating, because we wanted to rotate the images as well. And they said, oh yeah, maybe we can, we got to get permission. So they got permission, but then they realized they didn't have a big enough data set to work with because no one had ever gathered this much data of a total solar eclipse during one period. And so now they have it, so now they can have their machines learn how to recognize that. But the other thing that's tricky about the corona is it's semi-transparent, basically, right? And that's a really hard thing to do machine learning on in terms of aligning it. And it's changing also. So you're trying to align it with the big features, but not the small ones. So it turns out, again, to be a very difficult, even computer science problem. So you hit the difficulty on the head. And it's why, I can't sit here and say, and we discovered this brand new thing about the sun, because we're still dealing with that issue. Also, we had some amateur astronomers who know how to flat field. They know dark, so flat field. You want to know what your CCD is. Basically, the pixels are going to light up kind of because they get hot, and you want to know what that is. And then, and that's I think the dark. And then you also want to know kind of how the lens is affecting your image, your lens, so the equipment. And so there's ways of doing that too. And those two things, the amateur astronomers know how to do that. They do that all the time. But the public, who's never taken a picture of the sky ever, not even of the moon, we had these online trainings to teach them just how to point and click and get the data. And we didn't get to the flats and darks. So we hope to get to that, but we have some from some of the amateur astronomers. So I think we have the data we need, but it's going to be tricky. Yeah.
And the pictures you showed from NASA using a filter, you said it's too large. Is there any efforts NASA to take pictures using the moon as a filter from outer space, preferably in the ultraviolet?
Yes, they have done some of that, and you can find those images. But you still don't, the moon, it's hard again to line up the moon with the sun even out in space, so you have to be in just the right place, and that's hard, and nobody's convinced NASA to pay for it. Because you have, right, because it costs a lot in fuel to reorient satellites, and the more fuel, the more it costs to get it off the ground, and it kind of has a cascading effect. So no one said, we would learn this, and that would be a Nobel Prize winning thing if you did this. And so people just say, it's not worth it. It's a good question.
So kind of to bounce off of Ernest's question earlier about the trying to go through and verify the data sets, and then the answer that you gave with the rotation and trying to figure out exactly where it was. Is that one of the reasons why you mentioned that star being in the background was such a nice little thing, so you can go, all right.
Exactly. So for those of you who didn't catch that, very good. My talk has little nuggets like that throughout. You can rewatch it. Yeah, so here's that star, and that is exactly why I pointed that out. So we were really blessed to have, we're lucky to have this star that now we can align. And we're using, if you go to the Zooniverse, Citizen Science, what we're asking folks to do is click on the star. Because it also turns out that, so we have this nice Python software that does this orienting the image in a certain coordinate system. But it turns out that relies on some other data set that isn't quite accurate enough to always have the star in the right place. And so we're having people click on the star to reorient it. And then I think we'll be able to get better data for the Python code, so we can then get back.
So you pioneered on the machine learning end of everything, and you pioneered on the new data set for, that's really interesting. So after this,
right.
The next one that we're expecting was what again?
2024.
Do you think that that's going to cause a lot more ease of use with the data from that eclipse?
I do, because now what's happening is some of the scientists who've been part of this project or heard about it and got excited about it, they're actually now trying to get folks in, like the next trying to get folks in Argentina and Chile to do this, which is the next eclipse. And so I think that there will be people getting excited about this all the way up to 2024, and we'll just grow the database and we'll know more and more, and then it'll be like, everyone will say, oh, that was so easy, of course you did that. Isn't that how it works?
Where would be the this axis of the sun in that image?
Right, that's a good question. This, you mean I'm pretty sure it's right here.
Would be up.
Yeah. So it's been oriented for North Pole up in this image. Yeah.
Sounds like you could write an app to have the phone take the pictures for you in just the right settings and then send them to you.
Yes, and in fact we managed to get some funding to do that. And again, it turned out to be harder. Like, if you go look at the documentary, you'll see I'm holding my phone, and it never took the picture. But I had tested it, and it went. Anyways, my app didn't work, but it worked on other people's phones, right? So the trick was we got funding for that. Most people would say, that's 5 years, that's 3 years away, that's 2 years away. Oh my God, it's six months, okay. And then our poor app developers were like, we have 6 months to do what? And we wanted every cell phone that could take a photo to have this app. So that meant Android and iPhone, and iPhone has this whole this very tricky process, which we went through, and the iPhones had it, but not all of them worked. So again, we pioneered that, but now we have an app and we can work on it. Yes.
In that syncs time sequence, takes location data, and
right.
Does zooming and stuff.
Yeah, the trick with the app is that the little lenses really aren't very awesome. They have a lot of, I forget, what's the technical terms for when they have little blips and aberrations. Yes, thank you. They have a lot of aberrations. And and they're not very big. So they did way better than some people thought. But we also, a lot of people put little lenses on them. But then you had 2 lens systems, so that creates different aberration issues.
It doesn't work, the app doesn't know that.
Right. And so it was tricky. But we have all that data set too. And we're also looking at that. So, yep. And who knows what the phones will look like in 2024. Maybe they'll all be stuck here in our heads. Not in my head. Yeah.
You want to show your movie?
Do I want to show my movie? You mean of me screaming?
Yeah.
I hear this as a request. I will. Okay, let's see if I should be able to get on here. Again, this was a last minute thing. Someone at Google, I guess they do little documentaries at Google of their stuff. And someone heard about this project and they said, 2 weeks before the eclipse, and they said, some boss somewhere said, go make a documentary of that. And the documentary guy who was in charge went, okay, let's do it. And everyone said, you can't do that. There was a lot of you can't do that in this project. Impossible. 2 weeks, a documentary. So I'm not going to show the whole thing. It's 15 minutes, but here's how it starts. We'll do like start, middle,
Eclipses
end.
have shown up in cultural stories for millennia. In olden days, people would make up myths and they use deities to explain this natural phenomenon. There's kind of this natural ingrained wonder.
The eclipse itself is this bizarre moment when in the middle of the day, the sun just goes dark, and it's sort of awe-inspiring.
So I just want to do a quick shout out for this person who's speaking right here. This is Calvin Johnson. So he's been the person at Google I've been working with, and he has been amazing. Like just steady when crazy things were happening within the project and out. Just like I just have to give a shout out to Calvin Johnson. he was great to work with.
It's been almost 100 years since we had an eclipse go coast to coast.
If you get
There's
into
the app.
that thin, narrow zone of totality, you will see days.
There's the shadow animation.
Completely block the sun.
Less than 10 minutes to totality.
Did you see me holding that? Yeah. Well, it should take a photo now. I'll jump ahead here. So we had this film crew. I mean, I'm a geek. I'm a physics person. There's a film crew following me around. I'm like, okay, I'll do it for science. So these are some more of our colleagues at Google. That's me. This was in the morning. It was like a perfect day. Look at this. I couldn't believe it. And we're up in Wyoming on this beautiful
I'm
view.
not particularly worried. We've kind of gone through most scenarios where something could go wrong. And
So this is David. He had to stay back at Google to run the code to make the movie, and his code didn't work right after we got all the images. And he goes, "I'm going home." Like this, so this documentary shows it, and I'm like, what does he mean he's going home? We premised a movie. But he came back and made it all happen.
So we're entering first contact and second contact.
I mean, he really made a miracle happen. It was amazing.
To totality.
That was the app. Did you see
We're
that?
racing the marine layer. It's still overcast here.
And then Uriah, he also was in the bunker. We call it the bunker. So they were down in Mountain View, not seeing the eclipse.
Yeah, as our team members out in Wyoming.
So a reminder, I still have to get them present.
They apparently just had first contact with the eclipse happening now.
So here we are. This is my job.
So we got one guy who's on the team that wrote a bunch of the code that's here, but then the other ones, yeah, they're back at home making sure that it all works. Which I know.
A lot of the images get rejected because they don't have a latitude, longitude, and date time.
That might be what's screwing us up.
You're resizing to put the sun in the middle, and then you're resizing again to make it the size you want.
So you're saying that now I finally need this down at the bottom?
Okay, I can't work if you guys are just standing there with cameras constantly. Yeah, you guys need to get out for a while.
It should all just work fine. They shouldn't have to do anything today, but just in case, they're there.
They're from Australia. I mean, Austria.
1 minute, 5 seconds.
Yeah, look, you can see the horizon effect. Wow.
Okay, it should come now. There it goes. It should come. Look at the horizon.
It meaning the shadow. So you can start to just see it.
Here comes the shadow.
I swear I did not know I was saying all that.
Oh, wow. Oh, that's insane.
Yeah, this is up. Unbelievable. Oh my God. That was unbelievable. That was so cool. Just the darkness all around, the stars coming out.
I could see the red from the chromosphere, from the hydrogen, right there.
Corona comes out. Incredible. That was out of control. No, I want more!
Oh, the shadow's leaving us. Come back.
It looks so dark over there.
Come back.
It's insane.
It's insane.
It's like something
Wow, wow, wow. Day, sun, and moon! The shadow coming.
It's a lot to talk about. There's a lot of adrenaline
I know. All right, so there we are.